In this video, we explore electron configurations and orbital diagrams in a bit more detail and show how both are closely linked to the structure of the periodic table. So here we have the orbital diagram for multi-electron atoms that we can use in combination with the Aufbau principle and Hund's rule to generate full electron configurations. For example, to generate the orbital diagram and electron configuration for the sodium atom, which has an atomic number of 11 and therefore has 11 electrons in the neutral atom, we start by filling the 1s subshell. We then fill the 2s subshell, then the 2p subshell in order and according to Hund's rule, and then finally we place the 11th electron into the 3s subshell. So this gives the electron configuration for sodium as being 1s2, 2s2, 2p6, 3s1. And we recognize that this part of the electron configuration is actually the electron configuration for the noble gas neon. And so we can write a condensed electron configuration by placing neon in square brackets and then having the 3s1 electron as the outer shell electron. Now what we're able to show is that successive filling of subshells using the Aufbau principle matches the structure of the periodic table, in that filling of S, P, D or F subshells actually corresponds to the S, P, D and F blocks of the periodic table. In other words, orbital diagrams and electron configurations appear to be different ways of representing the structure of the periodic table. Now let's examine this idea a bit more closely as we fill successive subshells in the orbital diagram for multi-electron atoms. We'll start with the first electron, which represents hydrogen, and it has an electron configuration of 1s1. Adding a second electron results in the orbital diagram for helium with an electron configuration of 1s2. Now the first thing to note about the filling of the 1s subshell is that when it is full, that is with 2 electrons, we have a very stable electron configuration. Now how do we know this? Well, we know that helium is very stable and tends not to take part in chemical reactions, which means that it has a very stable electron cloud. And it turns out that this stability is associated with the fact that the 1s subshell, and indeed the n equals 1 shell, is full. It turns out that stable electron clouds are actually associated with full shells or full subshells. Now the second thing to notice about the filling of the n equals 1 subshell is that only 2 electrons can fit in this single subshell, and they correspond to hydrogen and helium. So when we look at the periodic table, we note that in period 1 there are only 2 elements, hydrogen and helium. Now if we go back to our orbital diagram and start filling the n equals 2 shell, we do so by placing electrons in the 2s subshell. So that's number 3, lithium with the helium core, 2s1. Number 4, beryllium, the helium core, 2s2. And then we start filling up the p subshell, boron number 5, carbon number 6, nitrogen number 7, oxygen number 8, fluorine number 9, and neon number 10. Again, we note that the orbital diagram and an electron configuration for the noble gas neon has a full shell and full subshells associated with it. So neon, as I said, is a noble gas. It tends not to form compounds or be involved in chemical reactions and has an inherently stable electron cloud. So again, we see the link between full shells and full subshells with a stable electron configuration. Now the other thing to note is that these 8 elements here correspond to the filling of the 2s and 2p subshells within the n equals 2 shell. So if we have another look at the periodic table, we see that period 2 has 8 elements in it in total, 2 of them in the s block and 6 of them in the p block. So it seems that the n equals 2 shell that accommodates 8 electrons corresponds to period number 2 in the periodic table that holds 8 elements, and that these 2 elements in the s block actually corresponds to electrons filling in the 2s subshell, and that these 6 elements in the p block actually correspond to electrons filling in the 2p subshell. And we can keep going. We can keep filling up the orbital diagram, go to the n equals 3 level, so fill in the 11th electron there, representing sodium, number 12 representing magnesium, and then go into the 3p subshell, aluminium, number 13, silicon, phosphorus, sulfur, chlorine, and argon. Now again, we see that filled subshells are associated, and filled shells are associated with stability, and we know that argon is a noble gas and has a stable electron cloud, and it's the result of these filled shells and filled subshells. The other thing that we should note is that these 8 elements here correspond to the filling of the 3s subshell with 2 electrons in it, and the 3p subshell with 6 electrons in it. So again, if we go back to our periodic table, we see that there's a total of 8 elements in period 3, 2 of them in the S block, 6 of them in the P block. And again, it seems like the n equals 3 shell of an orbital diagram corresponds to period 3 in the periodic table, with these 2 elements here in the S block representing electrons filling in the 3s subshell, and these 6 elements here in the P block represent electrons filling in the 3p subshell. And we can keep going, get into the n equals 4 shell, so that's potassium, number 19, number 20 there is calcium, and then the next, and then we can see that those 2 elements there correspond to elements 19 and 20, the first 2 elements in the 4th period, and they are in the S block, and the 4s subshell was filling. So we get to a part in the periodic table where the next elements are in the D block, so starting from scandium at number 21 up to zinc at number 30. And when we go back to our orbital diagram, we see indeed that the next subshell to be filled is indeed a D subshell. It's the 3D subshell. So if we were to fill that 3D subshell, and it can accommodate 10 electrons, we're talking about those 10 elements there from scandium at number 21 to zinc at number 30. The next subshell to fill is the 4p subshell, and it can accommodate a total of 6 electrons, and those 6 electrons corresponding to these 6 elements here in the P block, elements 31 through to 36. And what we see here, these 18 electrons here corresponding to the 2 elements in the S block, plus these 10 elements in the D block, plus these 6 in the P block, corresponding to a total of 18 elements in period 4. And so what it seems is that the S, P, D and F blocks of the periodic table correspond to subshell designations in the orbital diagrams and electron configurations. And we can even break up these blocks into sub-blocks, if you like. So the 1s subblock, the 2s, 3s, 4s, 5s, 6s, 7s, etc. And then 2p, 3p, 4p, 5p, 6p, etc. on the right-hand side of the periodic table. And then in the middle of the periodic table, 3d, 4d, 5d, 6d, and then finally down the bottom 4f and 5f. So given that orbital diagrams and electron configurations are actually different representations of the periodic table, we'll see in subsequent videos how we use the periodic table to generate electron configurations, and therefore how we can predict many chemical and physical properties of elements based solely on their position in the periodic table, including how certain atoms bond with other types of atoms.